Welcome back, everybody. Today is going to be a quick video on certain special negative inversion scaling matrices and Dirichlet series of cusp forms. So we're going to consider these matrices W sub n, which have entries 0, -1, and 0. Now, these matrices normalize gamma sub 1 of n, in the sense that if you conjugate gamma sub 1 of n by W sub n, you end up back in W sub n. And so by the basic theory of modular forms set up earlier in previous videos, if f is a weight k cusp form of level n, then f bar sub k W sub n is also a weight k cusp form of level n. Now remember this notation here, f bar sub k wn, that just means the determinant of W sub n, which is n, over cz plus d to the k. So my c here is n, so I'll have nz plus 0 to the k, times f evaluated at the fractional linear transformation 0z minus 1 over nz plus 0. So here are the entries of my matrix. So this is basically like f of -1 over nz times some scaling factor. Okay. In fact, you can do better. Like a direct, easy calculation shows that if f is a weight k cusp form of level n and character chi, then f bar sub k wn is a weight k cusp form of level n and character chi bar. Okay, and that's even more specific information than I gave you here. Okay, so basically we're trying to relate like f of z if f is a weight k cusp form of level n, and f of -1 over nz for some positive integer n. Okay, so here's what we'll do. Let's let f of z, let's give it a Fourier expansion. Sum n bigger than or equal to 1, a of n q to the n, so we'll just call the coefficients of f a of n. And then f bar sub k wn of z, that's also a cusp form we now know. So we can give it Fourier coefficients b of n, let's say. So let's let a of s be n to the s over 2 times 2 pi to the negative s gamma of s times the Dirichlet series attached to this Fourier expansion, which is the sum n bigger than or equal to 1 a of n to the negative s. You're replacing q to the n by n to the negative s in typical Dirichlet series fashion. And we'll do the same thing for b of s, just n to the s over 2 pi to the negative s gamma of s. Again, gamma of s is just the gamma function. Sum n bigger than or equal to 1 b of n to the negative s, the Dirichlet series attached to f bar sub k wn. Okay, and these factors out front of the sums are motivated by conjecture 1 from last time. Okay, now these sums here can be easily seen to converge, absolutely, in some right half plane. And so let's look at some parallels with conjecture 1 from last video. The conjecture from last video was essentially that the L function of an abelian variety has an analytic continuation to the entire complex plane and has a functional equation relating its values at s to its values at 2 minus s. Proposition 9, so this is not a conjecture. A of s and b of s do have analytic continuations to entire functions of order 1 and do satisfy the functional equation a of s equals I to the k, b of k to the negative s, and I here is just the complex number I. By the way, what's an entire function of order 1? I used that term last time and didn't define it. It's a function that essentially behaves like big O of e to the absolute value of z as z gets large. Okay, and furthermore, this 1 here attached to the absolute value of z, this power 1, this is the smallest integer power for which this is true. That's what order 1 means. It's just a technical detail that's not that important for us. And so we have a of s and b of s, they do analytically continue, and they do satisfy functional equations relating their values at s and at 2 minus s if k is 2. If k is 2, we get a of s equals negative b 2 minus s. That's very similar to the conjecture for L functions of abelian varieties. It's just that we have two different series going on here, and we're dealing with series attached to cusp forms, or quote unquote L functions attached to cusp forms, and not L functions attached to abelian varieties. Nonetheless, this is promising. The proof of this is in CSS chapter 3. Speaking of L functions, why didn't I just call these L functions of my cusp forms? They sure look like L functions to me. The problem is you can't really call them L functions because it would be disingenuous to do so without knowing that these series here actually have Euler products. Remember, L functions of elliptic curves and of abelian varieties do have Euler products. They can be written as like products over primes of some complicated reciprocal expressions. That is really what it takes to be an L function. You want a sum formula, like you want a Dirichlet series sum formula, and you want an Euler product formula. We don't actually know that either one of these sums have Euler product formulas. And so we're going to investigate that over the next couple of videos. And we're finally going to start tying all this back into Hecke actions and modular curves and stuff like that, because to actually consider the question, do these have Euler products, we're going to have to look at the Hecke operators. Okay, and so I will begin that next video, and I'll see you then, and thanks for watching.